Yeah, so today we are going to discuss generalized inverse matrix and pseudo matrix of a, let's say, matrix, any kind of matrix A. So how do you find the generalized inverse matrix or pseudo inverse for any matrix, right? Okay, why do we discuss this topic? Yeah, so this is the reason. So let me explain the reason. Yeah, so we started discussing getting a solution or obtaining solutions to this linear system. Remember, right? So ax is equal to P. This could be a square or rectangular. So when you do research, you will get any matrix for here. So it could be square matrix, rectangular matrix, right? So then how do you find the inverse of this matrix? So basically, we are interested in so when we are interested in finding solutions to this system, so this coefficient matrix could be any matrix, it could be square or rectangular, right? So when A is when A is a square matrix, say A n by n, right? So there are two cases, right? So there are two cases. A could be singular or non-singular, right? Okay, singular or non-singular or invertible, right? Non-singular, right? So here's singular, right? So there are two cases. This A, if A is a square matrix, A could be, so non-singular, then we know how to find the solution if it is non-singular. If it is singular, we know that. If this is non-singular, we know that there is only one solution to this equation, this linear system, right? If it is non-singular, there is only, or unique, I will use this word unique. There is a unique solution. That means there is only one solution. There's a unique solution if this matrix is non-singular. If it is singular, so and let's assume this system is consistent. So that is very important. So let's assume under that assumption. So let's assume. So there's another case, another two case, consistent, inconsistent. Yeah, so first case consistent. Code, what, don't know what happened to my, this, consistent. And the other one is inconsistent, not consistent, no, inconsistent. Consistent. Right, you can, right. So there are two cases. This system could be consistent. If it is consistent, we know how to find solutions, right? And if this system is consistent and let's assume this matrix is square matrix, then we can break into two. So this matrix could be non-singular or singular. If it is non-singular, that's fine. Then in first 2 weeks, I think So during first 2 weeks, we found the solution. We obtained the solution to this linear system, right? If it is consistent and square matrix and non-singular, right? So let's assume, this system is consistent. Then A could be, this coefficient matrix could be singular. So then in that case, the system has how many solutions? So if for that case, so how many solutions are there to this system? Yeah. Now you can answer my questions. Yep. So last week we didn't have that facility messaging, or so you have to unmute. You had to unmute your mic and answer my questions. Yep. So what is so if this system is consistent, so I will explain this one later. What does this consistent and in seconds, right? So if this system is consistent and this matrix, coefficient matrix, is singular, so how many solutions are there to the system? Yeah. Anybody? Hurry up. So let's keep this as a dialogue. Yep. So how many solutions are there if the system is consistent and matrix is singular? Yeah. How many solutions? One or two? How many? Hurry up. Yeah, there are infinitely many solutions. Infinitely many. Yeah. So infinitely many. Yeah. I'll just say infinite. Many. Yeah. So many. I will say infinite. Yeah. Many. Yes. Many solutions. Right. So we haven't discussed this case. Yeah. Today and this case as well. So right. So we just so far we have discussed only consistent systems, and this is a square matrix, right? And non-singular, and that coefficient matrix is non-singular. Then we were able to find the unique solution to this system. So what if this system? So and what if this matrix is singular and the system is consistent? So we know that infinitely many solutions. So this system has infinitely many solutions. So I will going to cover this part in this section. So I will discuss this one, right, and the other one is this system is consistent, and what if this matrix is rectangular matrix? Let's say n times m, rectangular. So consistent system, and the coefficient matrix is rectangular. So then how do you find the solution? So I will address that one as well. So first one is this one, right? And another one is when A is a rectangular matrix of a consistent system. And I will discuss this one as well, inconsistent. So what if this system is inconsistent, right? So then we cannot find solutions, right? So if this system is inconsistent, so there are no solutions, right? I will discuss that one also. I will discuss that one also today. Today I will cover these three things. If the matrix is rectangular, the matrix is singular, how do you find at least minimum? What is the minimum solution? You have learned norms. So I want to find, so here we have solution set, right? Because there are infinitely many solutions to this system. So what is the, so this is the solution, one of solutions, right? So what is, yeah, so I want to find a solution which gives me a minimum, yeah, magnitude of this, magnitude of or distance between the solution and the origin. Origin, yeah, zero matrix is minimum. Yeah, let's say is the smallest. I cannot say smallest. Yeah, smallest one. Yeah. So mean x is, so this is solution set, right? Solution set. Solution set. Yeah, solution set. So I would like to, yeah, pick the solution which has, yeah, so smallest norm value. Yeah. No. Okay. And the other case, yeah, so I will discuss this one as well. If the system is inconsistent, so we know there is no solution, right? In that case, yeah, I will discuss this one as well. Okay, got it? Did you understand the objective learning objectives of this lecture? Yeah, did you understand that? Right. So we are discussing the system, right? So obtaining the solution of the system. So let's focus on this coefficient matrix. So this is our coefficient matrix. So this is the first column of the coefficient matrix A, second column, and how many? So this is a general coefficient matrix. It has n number of rows and m number of columns, right? So this is the first column, second column, and mth column, and these are elements in R M vector space, right? So so if you consider the spanning set of these column elements, these vectors, it is called the column space of this coefficient matrix A. Column space, spanning set of A1, A2, AM. So which is called, yeah, column space. Here, this is the variable, okay? X is a variable, right? So remember, so your X is a unknown, yeah. So X1, that X2, how many X's are there? So dimension should agree. So m number of x's. M number of x's. Okay. So yeah. So a times x is the spanning set. Yeah. Let me write. So vector a1. Yeah. So x1, x2, a2, hold the, yeah, this is the spanning set, right? So very easy if you understand the pure math. Normal. Those are simple. Yeah, so those are, yeah, so xn a m. Yeah, this is the all. Yeah, so So look at this. This set is your spanning set. This is the column space. This is, so we call this is the column space, right? If your B, this B on this, in this A, B on this plane, let's say B is included in this set, then we call, this system is consistent. Got it? If B is not an element of this space, so what if, so then B is not in this set, right? So B is outside of this set. So then you cannot find solutions, but you can find some X, right? Right. So here, so when you change this X variable here, you get different. Yeah. So look at the distance between B and its projection. No. Distance between B and that point, AX. So if X is here, so you have this length, distance between B and AX, and distance between B and AX. And you get the minimum distance. So we find basically the minimum of X. Yeah, in solution space. Yeah. So basically we answer, we will find the optimal one. So we will find this here. We find this X star, which is the minimum of this cone. Okay, so this is called the least square method. So that makes sense if you conduct a research, you will get a huge number of data points, data set, right? Big data set, right? So let's say you have a huge list of data points here. Okay, this is your, if you do some kind of perform some kind of experiment, so you get this kind of big data set. So let's say you want to find a representative of these data points or data set. So when you find that, so let's say you are going to find a baseline or linear line that represents this data set, right? So this line does not pass through all points, right? Here. So this line is not going through any point, but so that's why, so if it is going through any point, so let's say, so you have few number of points. If this line going through all these points, then a x equal b exactly, then you can find this straight line. But here you cannot find a line which passes through all points, but we can find a baseline that represents this data set. So that is this problem. So you are finding the least square of this, basically. The solution set, right? Solution set. So does that make sense? These column elements of these column elements of R n. Someone is asking a question. these column elements in Rm. Sorry for, yeah, so how many rows are there? Yeah, sorry. Yep, so here we have m number of elements. So dimension should be Rn. That was my mistakes. Thank you. And this should be Rn, right? So here we have how many elements? 1, 2, up to m. But the dimension is how many? So this is the dimension number of rows. Entries here n number. So these are elements in Rn. So this is a subspace of Rn. So this is a subspace of Rn, right? So this is the spanning set, the spanning set of these column elements, columns of matrix A. So this is called the column space of A. Right? If your B in this set, you can find X very easily. That means that system has solution. If your B is outside of this space, column space, you cannot find solutions. But you can find the distance between this space and this point. So what is the minimum distance between this point and space? Which is the projection, orthogonal projection. So yeah, so this length. Yeah, so then you can find the corresponding x. Here, when you change x, you get different ax, right? So when you vary x is a variable. You vary x, you get different points in this space. So what is the minimum length of this this vector? So minimum length is the orthogonal projection to this space, column space. Got it? Is that clear to you? So this is the big yeah, this is the lecture outline. So we will discuss generalized inverse of a matrix, and then we discuss pseudo inverse of a matrix, then application to so this is the main application, this one, application solving the equation. So equation solving, so we can find solutions when B inside the column space of A. If B is not in the column space of A, we cannot find solution. There are no solutions to the system, but we can talk about this least square method. So minimizing this, can find the minimum x. Now we can find x such that this distance, this space, this column space, the distance between this column space and this point outside B is minimized. A is minimized. So we can we can find this corresponding x so that B and this space, column space, so that we have the minimum distance between this column space and this outside point B. Got it? All right. Is this clear to you? Right. Recording now. Yep. So recall. Yep. So if you have a square matrix, as I said before, which is invertible. So if the X is a square matrix such that, so left and right. So this is B is the both side, left and right should be. So when you multiply A by B, you get identity. So it's called the inverse of A, right? B is called the inverse of A. So so these are. So we know that earlier, you remember. So I think you remember On the first day, so to check the invertible matrix, we found the rank of A. So if it is full rank, then so that matrix is invertible. Or you can check, either you can check, yep, so whether this determinant of this matrix one, so determinant is